Okay, yesterday we talked about pressure and temperature converting between Celsius and Kelvin, and then we talked about Boyle's law, which was the relationship between pressure of a gas and the volume that it takes up. So today we're going to be talking about a couple of other laws that tell us how gas behaves, and the first one of them is what's called Charles' law. Right? And Charles' law has to do with volume and temperature instead of volume and pressure. So if you guys were here last year at Guama, you might remember the cryo day experiment that we did, where we passed out liquid nitrogen to y'all, and you got to play with that and dry ice and dip stuff in it and see how it froze and all that. But one of the things we did was we had y'all blow up a balloon and then dunk that balloon into the liquid nitrogen. And what happened when you did that is the air inside the balloon kind of shrank down. It started taking up less volume, and so the balloon, instead of being nice and big and blown up, it got shrunk down into a smaller volume. All right, and that kind of shows us the relationship between temperature and volume of a gas. So what happened with the liquid nitrogen was that as the temperature decreased, the volume decreased as well. And that works the opposite way. As temperature increases, the volume will increase. So this is kind of the opposite of the law we talked about yesterday. So with that one, they were inversely proportional, where when one of them increased, the other decreased. In this case, for volume and temperature, when one of them increases, the other one increases as well. And you can see that with a little graph here, where as volume goes up, your temperature is also going up. They go up together. Okay, so the reason that is, as these gas particles are heated up, they start to have more kinetic energy and they move around a little bit faster. That causes them to expand and take up more space. All right, the way this is written as a mathematical equation is, instead of having in Boyle's law where we had our two variables multiplied by each other, on this one our two variables are going to be divided by each other, right? So instead of V1 times T1 like we had yesterday, these are going to be V1 divided by T1. So this V1 is our initial volume, and T1 is our initial temperature, and then V2 is the final volume, and T2 the final temperature. Okay, so to solve these problems, if we look here at this, what it's telling us is that we have a birthday balloon filled with a volume of 1.5 liters of helium gas in an air-conditioned room at 293 degrees Kelvin. Okay, so we know our initial volume is 1.5, so we're going to plug that in here. That's our V1, and we're going to say that's over our initial temperature, our T1. So 293. And here, I'll write the equation up here. Okay, and we're going to say that is equal to, after the balloon is taken outdoors on a warm day, they say it expands to 1.55. So that's going to be our V2, our final volume, and we don't know our final temperature. Our final temperature is unknown. It's T2, a variable. All right, so there's two ways we can solve this. We can multiply or divide these two and then, multiply like regular algebra to figure out what our variable is here. Or if you recognize this kind of format from when we talked about mole ratios and stoichiometry, we can solve this the same way we did those, where we use cross multiplication or the butterfly method. I think that's the easier way, so that's the way that I'm going to do it for this example. But if you're not comfortable doing that, you can do it the other way as well. So here, if we do the cross multiplication, we're going to do 1.5 times T2. So we get 1.5 times T2. And we're going to say that is equal to our 1.55 times 293. Okay, so then we've got to multiply these two together. So 1.55 times 293 is 454.15. All right, and then to get T2 all by itself, we have to divide both sides by 1.5 in order to cancel it out over here. So we're going to divide this by 1.5. And so our final answer of the temperature outside is 302.77 degrees Kelvin. Or just Kelvin, no degrees. Okay, the one tricky part about this problem, after you solved it, is that the problem is actually asking you for the temperature outside in Celsius. So you guys have got to remember, when you're converting from Kelvin to Celsius, you're going to subtract 273. So we're going to take our answer here, minus 273. And so we can say that it is 29.77 degrees Celsius outside. All right, another example problem here. This time it's telling us that we have a beach ball being inflated. And let's write out our equation here. We've got V1 over T1 is equal to V2 over T2. That's the general form that all of these Charles law problems are going to take. All right, so we've got a beach ball inflated to a volume of 25 liters of air at 15 degrees Celsius. And during the afternoon, the volume increases by 1 liter. It wants to know what the new temperature is outside. Okay. So the tricky thing here, every time we work with temperature with our gas laws, we always want to convert from Celsius to Kelvin before we plug it into our equation. So remember, if we're going from Celsius to Kelvin, we're going to be adding 273 to it. So 25 plus 273 comes out as 298. So 298 is going to be our T1, and our initial volume is 25 liters. So we're going to have 25 over 298. All right, and we say the volume increases by 1 liter. So that's kind of some tricky wording there. A lot of y'all I know would want to just put in 1 liter. But if it's increasing by 1 liter, that means it's going up 1 from 25. So our new volume is 26. So pay attention to stuff like that. Don't get caught by it. And we're looking for the new temperature. Or, sorry, I drew that in as X, but it really should be T2, I guess. All right, so to solve this, we're just going to do cross multiplication again. We've got 25 times T2 is equal to 298 times 26. And then to get T2 by itself, we have to divide both sides of this equation by 25. So here, 7748 divided by 25 gives us 309.92 Kelvin. All right, and this one doesn't ask you for a specific one. It doesn't ask for Celsius or Kelvin. So you could leave it like this and you'd be fine. Or you could convert it to Celsius if you wanted to by subtracting 273. And then you'd have 36.92 degrees Celsius. So either one of these two answers here is fine. All right, so that is Charles' law. It's the relationship between volume and temperature when pressure and mass are kept the same. All right, we have one more law that we're going to talk about, or one more of these simple ones, and it's called Gay-Lussac's law. So we've talked about pressure and volume. We've talked about volume and temperature. So really the only combination left there of those three is temperature and pressure. So if we have a balloon inside a container that ensures it has a fixed volume. So you've got your balloon and you put it inside of a square box, right? Where the balloon can expand to fill up the box, but then no more. It's stuck at that size. All right, so you heat up the balloon. It can't expand. So earlier in our last law, we related volume to temperature, and we said that when temperature went up, volume was supposed to go up. But if this balloon is trapped in that box where it can't actually expand and gain volume, what do you think is going to happen to the pressure inside that balloon if it wants to expand and it's not being allowed to? When you have a situation like that, your pressure is going to increase. So that was Gay-Lussac's law. He says if the volume and the mass are held constant, the pressure and the temperature of a gas are directly proportional. So as one goes up, so does the other. So this equation is going to look a lot like Charles' law. Instead of volume over temperature, it's pressure over temperature. So the way you're going to do that is P1 over T1 equals P2 over T2. You're just substituting out the volume for pressure in this equation. There's a little video here. I'm not going to show it in this, but you can go and watch it yourself. That shows an example of this relationship. All right, so we can see here an example problem. And we're going to do this the same way we did the other ones. We'll write out our equation. So we've got P1 over, nope, not V1, over T1 is equal to P2 over T2. And then we can start plugging stuff in. We know that the initial pressure of this gas inside whatever canister they're talking about is 5 atmospheres. So that gets plugged in for our P1. All right, and it's at 15 degrees Celsius. So just like in the last one, we can't use it as degrees Celsius. We've got to convert it to Kelvin. So to go from Celsius to Kelvin, you add 273. So we've got our initial pressure over our initial temperature. We're going to say that's equal to our final pressure that we don't know. That's what the question is asking about. The pressure of the oxygen gas once the temperature is 263 degrees Kelvin. So again, same as on the last one, all we've got to do here is cross multiply. We can say 5 times 263 is 1,315 and that is equal to 288 times P2. To get P2 by itself, we divide both sides by this 288. And that comes out as 4.57 atmospheres of pressure. So our temperature went down from 288 to 263 Kelvin, so we should expect that our pressure goes down as well, which it did. It went down from 5 to 4.57. So this checks out logically. All right, let's get rid of all this stuff and try one more example problem. So again, we're using the same equation here. P1 over T1 is equal to P2 over T2. All right, and it's telling us that the pressure of a gas in a sealed canister is 350 kPa at a room temperature of 15 degrees Celsius. So that's our initial temperature and pressure. Again, the Celsius, we're going to have to convert to Kelvin. So we do that by adding 273. So we end up with 350 kPa over 288. All right, it says the canister is placed in a refrigerator that drops the temperature of the gas by 20 Kelvin. So again, this one's a tricky one like the last one, where it said it increased the volume of the beach ball by 1. So our new temperature isn't 20 Kelvin. That would be like the world's coldest refrigerator. Our new temperature is this one minus 20. So it's 268 degrees Kelvin. All right, and our P2, we don't know. That's what we're trying to find out. So same as last time, we've got to do some cross multiplication. We're going to take our 350 times our 268. It's going to give us this big old number here, 93,800. So that's equal to 288 times P2. Okay, then we've got to get P2 by itself. So we're going to cancel out the 288 by dividing it on both sides. So over here they cancel out. And our answer is 93,800 divided by 288 tells us our new temperature is 325.69. kilopascals. Okay, so same thing as last time. Our temperature went down, so we should expect our pressure to go down. And it did. It went down from 350 to 325. So we're still on the right track there. All right, the last law we're going to talk about is the one that throws all these things together. It's called the combined gas law, and you get it by combining all three of them together into one big equation. So we've got Boyle's law of P1V1 equals P2V2. We've got Charles' law of V1T1 over V2T2. And then we've got the Gay-Lussac's law of P1T1 over P2T2, all put together into one big honkin' equation like this. So this comes in handy when you've got more than one variable changing at a time. All right, so in this one, it wants to know if a gas occupies 7.84 centimeters cubed at 71.8 kPa and 25 degrees Celsius. It wants to know what the volume will be at STP. So remember we talked earlier, STP, we mentioned it yesterday. It's equal to 0 degrees Celsius and 1 atmosphere of pressure. All right. And if we go back and look, I'm not sure what slide it's on, so I'm not going to go find it right now. But in this PowerPoint somewhere, we have a list of all the different units of pressure. Here in the problem, it's using kPa. So we want to convert this 1 atmosphere to kilopascals. And on that slide, it would tell you that 1 atmosphere is equal to 103.25 kilopascals. Sorry, that didn't sound right, so I just went and checked actually. And it is not 103.25, it's 101.325. So let me erase this real quick. It's actually 101.325 kilopascals. And then obviously we're going to have to convert Celsius to Kelvin. So just like we've been doing, we're adding 273. So our temperature at STP is 273 Kelvin. Okay, so we know these are going to be our P2, our P2 and our T2, and we're looking for the final volume. So our equation was P1 V1 over T1 is equal to P2 V2 over T2. Oh, that came out weird. And we're just going to start plugging stuff in. It gives us our initial volume here, our V1, and our initial pressure there. So P1, 71.8. V1 is 7.84. And our T1 is 25 degrees Celsius, which needs to be in Kelvin. So we add 273 to it to get 298. Over on the right side, we know P2 is the standard 1 atmosphere, which is 101.325 kilopascals. Our V2, we don't know. That's what we're looking for. So it stays a variable because it's asking about the volume. And we know our temperature is 273. Okay, so easiest way to do this is still cross multiplication. So we can take all of these here, and because these are just being multiplied by each other, we just make this one big multiplication string. 71.8 times 7.84 times 273. Comes out as 153,674.98. And we're going to say that's equal to 298 times 101.325 times V2. So 298 times 101.325 is 30,194.85 times the V2. And then same as the last time, in order to cancel this out, we have to divide by this whole number here to get V2 by itself. So divided by 30,194. I'm kind of running out of room down here. 0.85. All right, so we're taking the 153,674.98 divided by 30,194.85, and that should be our answer for V2. So this one gets a little bit complicated because you end up working with these really big numbers. But it comes out as 5.09 cubic centimeters. All right, and that kind of makes sense, right? Our pressure increased, which we think should decrease the volume, and our temperature decreased. It went down from 25 to 0 in Celsius, which should also decrease the volume. So both of those decrease the volume, so we should have a smaller volume than we started with, which we do. So logically, it all works out. Oh, let's get rid of that. All right, and then the last thing is going to be questions where you're given just some information and you have to figure out which law to use. So this is where you're going to have the most trouble, and you'll have to do a little bit of thinking and figure out, what is it giving me, what do I need to know, and which law can I use to actually solve that. So on question A here, you've got a gas occupying 473 centimeters cubed at 36 degrees Celsius. So it's giving you volume and temperature, and it wants you to find the volume after the temperature changes. So the only two things you're worried about here are volume and temperature. So we can go look back through our laws and find the one that relates those two quantities, which was V1 over T1 is equal to V2 over T2. Oh, that's pretty ugly. Okay, so we can just start plugging stuff in here. We've got a volume initially of 473 and a temperature of 36 plus 273, because remember, we always have to convert it to Kelvin. All right, and that's equal to V2 that we don't know over 94 plus 273. Because that's our final temperature. And then we just cross multiply. 309 times V2 is equal to 473 times 367. Is that right? Yep. And then to get V2 by itself, we're dividing both sides by this 309 to cancel it out. So our final volume here is going to be 561.9 0.78. So the actual math itself there is nothing new. It's the same law. The only thing you've got to realize, or the only new thing, is figuring out which law to use to solve the problem. Right, part B, it's giving you pressure and it's giving you temperature. And then it wants to know what the new pressure or what the new temperature will be at a different pressure. So we need to look for the law that gives us a relationship between pressure and temperature. So if we go back and look through them, we should find Gay-Lussac's law is the one that has to do with pressure and temperature. And that one is P1 over T1 is equal to P2 over T2. Dang, I don't know why my mouse won't work. Here we go. So all we're doing again here is plugging stuff in. Our initial pressure is this 765 torr. And our initial temperature is 23 plus 273 for a total of 296. We're going to say that's equal to this pressure here for P2 over some unknown T2. Alright, so we get 765 times T2. Oh, that's going to be too low, isn't it? And we can say that is equal to 296 times 560. Alright, then to get T2 by itself, we cancel out the 765 by dividing it on both sides. So it cancels out over here, and we get this divided by 765, and we come up with our new temperature of 216.68 Kelvin. Alright, so that's all there is to it. You guys have a couple assignments today over these different gas laws. And then once you get done with those, just again, try and make sure you're all caught up with any of the old stoichiometry stuff that you haven't got done. Let me know if you have any questions.